The claim here is that the nature of this particular group will influence the most favorable place for the NO2 group to end up. Because we could either replace this hydrogen ortho to CF3, this one meta to CF3, or this one para to CF3. And so the first part of this problem is for you to think about what is the electronic nature of the CF3 group, and recall from last semester that anytime there's a fluorine in a problem, there's a particular thing that you should really home in on. Some property of fluorine that will often be the key to the problem. The property of fluorine that is key to this is its very high electronegativity. Fluorine is the most electronegative element. So this group right here, the CF3 group, is one of the most famous examples of an EWG, or electron withdrawing group. And so what I'd like you to think about is, would you like to follow a path where whatever positive charge you generate, because remember you're going to generate a positive charge somewhere on the six-membered ring, if CF3 is electron withdrawing, would you like to follow a path that gives you the positive charge right on the carbon that has the CF3 group attached, or would you like to avoid having the positive charge right on the carbon to which the CF3 group is attached? So think about that. Hopefully you decided that the last thing you would want to do is to put a positive charge on this carbon to which a thing that is already electron withdrawing is attached, because a positively charged carbon is already electron deficient, and energetically it's got to be a bad thing to have an electron withdrawing group attached to it. Okay? So the pathway that we're going to want to follow here is, again, as in the previous example, the meta path. So draw a mechanism for electrophilic aromatic substitution of this benzene derivative. This would be trifluoromethylbenzene. Following the meta path, draw out the mechanism and write the final product. So that's your job. So to follow the meta pathway, we could use this double bond here. We're going to use this double bond to add to the nitronium ion. And then we can't just make a bond in nitrogen because we would exceed the octet on nitrogen, so we have to do something like that. And remember, we've guessed that we should follow the meta product, and we'll see why in just a second. So in this case, we would want to have the nitro group, this NO2 group, connected to the meta carbon. And so we would end up with that intermediate, and the positive charge is here. So now what I want you to do, if you're not convinced already, draw the other two resonance structures of this cyclohexadienylcation intermediate and verify that the positive charge in those resonance structures never resides on this carbon that has the CF3 group directly attached to it. We would do the usual thing, move the electrons around in this way. I'll just abbreviate this NO2 group as NO2, like that. CF3 here. Positive charge moves to that carbon. And then one more resonance structure. Here we go. So notice, this pathway is favorable because it avoids plus charge on the carbon that's directly attached to the CF3 group. Nowhere do we have a resonance structure with the positive charge at this carbon. So in a sense, this is the least bad scenario. You might want to verify for yourself as an exercise. What if you follow the ortho pathway? What if you follow the para substitution pathway? What you should find is that in both of those alternative pathways, the positive charge does in fact end up on the carbon that has the strongly electron withdrawing group. So in terms of the relative energetics of these possible pathways, the meta pathway would be lowest in energy, would occur fastest, and as a consequence, we would expect the meta product to predominate here. So just to finish off this problem-solving video, the last thing you need to do is to show how you would finish this mechanism to go from the cyclohexadienyl cation intermediate to the final electrophilic aromatic substitution product. Remember that that involves a final elimination step, removal of a proton from somewhere. You show from where. Here's a common problem. People remove the proton from the wrong place. You have to find the carbon that has a hydrogen on it, but there are various ones that have hydrogen on them, like this one, and this one, and this one, and this one. Find the one where the hydrogen is attached to an sp3 carbon. This is the hydrogen that you want to remove. What is the base? Well, it's X minus in this particular example. So if we use X minus to remove this proton, and at that point we can make a double bond, and we would have to push the arrow around that way. Notice you could do this from a different resonance structure if it's easier for you. So I would get to the same place if I started over here, removed this proton, and did that. Or you could work with the third resonance structure. You would remove this proton and put the arrow there. Notice it's the same proton I'm removing in any of the ways of drawing this. The double bonds in the benzene ring might end up in different positions, but you know that's okay because of the Kekulé structures. So the final product is going to be this one, in which the nitro group has replaced the original hydrogen at the meta position. Okay? The take-home message from this final example is electron withdrawing groups, like CF3, will direct, that is encourage, electrophilic aromatic substitution at the meta position. All right, see you in class.